Let's continue. Yes.
When will we discuss the more? When will we discuss the
we have 2 classes now, yes? In the second class. So now I want to continue our Openmp class and to show you 4th task. 4th. 1, 2, 3, 4. For task, Openmp task, okay.
The last homework of the semester.
The last homework. They are very small.
Oh, okay.
No?
Huh?
Do you agree or no?
About what?
About that the task rather simple. No?
Which one, sir?
First, third.
First, yes. Third, not that much, sir.
Not okay. And what about second?
Oh, second is the hardest one.
Okay, so we have stopped, as I remember, here, I suppose. Okay, here. So what I want to say is that when you use Openmp and directive like this, Pragma OMP4, for example. So when threads.
Is it possible to increase the brightness? Okay.
So when we are in the parallel part, here for example, yes, here in the parallel part there are a lot of threads, maybe 2, 3, 4, 5, 10, 12, 20. So maybe it's up to you, maybe it's up to the system, operational system. So default number equals to number of available processors. So when a lot of threads are here and they enter the for loop statement, so when they work here and go out for loop, here will be the implicit synchronization. So every thread will wait for other threads. But maybe you want every wait doesn't wait for others. Maybe, for example, for that you can use key named as no wait option. In this case, every thread will not wait for others. It's I suppose, rather simple. What about collapse statement, collapse option? This option is for nested loops. When, for example, 2 or maybe 3 nested loops, and you want to parallelize even loops which are inside. So how does it work? Here, for example, sample for nested, I suppose. Yes, maybe here I'm thread as my And S++, I suppose here we should comment. So because of I cannot connect the remote server, so there is some code that was here. So here you can see nested loops. For example, I want to set here, let it be one thread. Let it be firstly one thread and nested loops. Here you can see that S and some variable, and S is a private variable. Okay, initial value of this S equals to 0. And here we increment this private variable. How many times we will increase this variable? How many times? 2000, yes. 2 times in the outer loop and 1000 times in the inner loop. So if there is just one thread, there will be just one print out statement. I'm thread number, my ID. Prag member critical can be commented. So let's run it. Will it run? I don't know how. Can you see? So parallel part, and thread number of threads equals to 1. Okay, and thread 0 and S equals to 2000. Okay, that's okay. Just do not look at this two lines. Is for okay. Let set number of threads equals to 2, for example. So we can see that in the parallel part there are 2 threads, and every thread increases 1000 times. Okay, what will be if we take 3 threads?
So it's going to be 3 divided by 2000, and each one's going to increment by so much.
Any other opinions?
I think 0666. Sorry. Yeah. One will also have 666, and thread 2 will also have 666.
Let's see. So 3 threads and 2 loops, 2 nested loops. Outer, inner, okay. Outer 2.
Then maybe it's going to be 1000 and 1000 and 0.
Maybe.
This may mess up.
Why is it so?
Well, because there's on the outer loop there's only 2. We're just going to access the 2 threads, and then the third one is going to be empty.
Okay, let's see. Maybe you're right. So 3 threads.
Thanks.
Thread number 1, 1000. Thread number 2, 0, and thread number 0, 1000. Why is it so? Because they divided just outer loop. Because outer loop consists of 2 steps, we cannot divide 2 on 3. Yes? So one thread takes just one step in the outer loop, and the inner loop will be fully inside one thread. The second thread takes this second step of outer loop and full inner loop. And so we have 2 1000 iterations inside these two loops, and they were divided, these iterations were divided just by 2 threads, and there are 0 iterations takes by 3rd thread. What will be if we turn on this option, collapse 2? Let's see. Same thing, but it is strange, by the way. No, it's been changing. This is strange. I mean, 3 threads, collapse. Was it compiled? I suppose yes. Okay, let it be 4 threads. Strange. I and G is private, okay, that's good. S is private, collapse 2. By the way, it's strange. Maybe because of this compiler inside my Visual Studio, because it's a local compiler. Why? Maybe in this. It seems this one. Very good. So let's try to launch it. Openmp simple. G++, Openmp simple. F. And let's change these, uncomment this, so we can see that. Let's try 4 threads and collapse 2, and here should be 2, for example. Let it be a lot of, and here we can change 1000.
So everything's going to be 500.
500, yes, and here I have a thread, and I suppose my time here, my ds S is a small double No. Why S is so strange? 15. I mean, 500 it's okay, but why is it? 1000. It's okay, 1000, but why these numbers are here? I see. Maybe because we have calculated here something, and we should say here S equals to 0. So okay, it will be okay now. So I don't know why, but in my local machine, option collapse doesn't work. Now we are on the remote machine. If there is no any collapse statement, that means we use 4 threads. 4 threads. We can see just 2 threads are working, and 2 threads without any work. So if I turn on collapse and use 4 threads, we can see that all iterations of all loops firstly were summarized and then divided between all threads, all 4 threads. If I use not 4, but for example 6 threads, where is it? Settings. I cannot use here because I'm on client machine. Okay, it doesn't matter. So we can see. Okay, 3 threads. Let it be 3 threads. Okay, we can see with the collapse.
So it cannot be 666.6666666.
Of course not, because the number of iterations inside loops, this is integer. Integer. It cannot be divided.
Doesn't it add up to more than 2000?
So if we summarize these numbers, we get 2000.
Yeah, exactly. Okay,
so all 2000 iterations that were inside every loop, 2 loops, they were divided between available threads.
But how does it know to divide to, let's say if we want to give 667, does it use the same amount, the same code that we use in our first form? Like to divide?
We can, okay, here inside Openmp, we can influence on how the iterations of loop, inside loop, can be divided between threads a little bit. I will not go on. I'm not going to discuss about how, because maybe later, if you want, we can discuss. But this is a little bit complex. By default, this division of iterations between threads works like it was in your first homework, just in the same way. That's why the remainder was distributed between first threads, like it was. So it almost the numbers, you can see the difference between numbers no more than 1.
Yes, sir.
So the division is rather good by default. So maybe we can, or maybe it's even not worth to discuss. Maybe I don't. By default, it's rather okay. So collapse. When you use collapse statement, you divide all loops, divide iterations of all loops. Why is it maybe important? Can be important. For example, outer loop contain steps less the number of threads, and if in this case you do not use collapse, that means some threads will not work. But of course, the operations inside should be independent of each independent from every operation should be independent from other operation. They should be independent. So collapse can be useful. It depends on the task, on the geometry maybe of your task, and so on. Okay. Do you have questions? Okay. What about synchronization? We have this.
For collapse, so if we had 3 for loops nested in one another, it's going to do the same thing.
Okay. Let's see. How many? Let it be 10. Yes. Okay. Inside 10, so it should be 10,000, 20,000, yes? 20,000. No. Here. Okay. We can. Oh, okay. That's a good example. So I try to use key. It should be private. So there is no any key before. I have not declared this key. We can see here. So I can declare inside parallel part int k even equals to 0, and in this case k automatically will be private. So we can see if I use 3 threads and use and do not use collapse, we can see that as it was before, 10,000. So 20,000 divided, distributed between 2 threads. Okay, let's turn on collapse, but 2. We'll see what will be. So we can see, no, we have to, okay, to change here, should be 1 and should be like this. Outer loops should be, the steps of outer loops should be less than number of threads. Let's see like this. Firstly will be the same, almost no. Okay, 10 10. It's okay now. And then how to make good example. I have divide because if two threads here, they divided outer and they go down and every thread takes the whole parts. How to make good example to collapse 3? Wait a minute. Okay, maybe I will wait in the break how to show that collapse 2 is somehow different from the collapse 3, because now it seems that they will be equivalent in this case. So it's rather so I cannot do it right now. So okay, I will think in the break. Let's continue. So yes, if there is, for example, let's just see that it will work. If collapse 3, we can see here. So it works now. Let's think. Okay, now it's working. So if how many threads here are? 3 threads. Okay, I see. 3 threads. 3 threads. So 3 threads. If we use collapse 3, that means we summarize all 3 loops. 1000 here, 1000 here, so it will be 2000, 2000 between 3 threads. It will be like this. Okay. If we use collapse 2, we divide 2 steps of two outer loops. We do not consider this inner loop. So we have 2 steps between 3 threads. It will be just 2 steps for 2 threads and 0 step to third thread. So 2 threads working, and they takes, one thread takes 1000, and the second thread takes 1 and 1000. So okay. Okay, 1000, 1000. So it makes sense to use collapse 3 like this. Okay, go further. So I just remind you about 3 categories or 3 classes of Openmp directives. Parallel scope definition, where there is a parallel part of your program where a lot of threads can exist. Work distribution, because the main work is inside for loop statement and while loop statement, so this work should be parallelized. But when you use while loop statement, the system, I mean Openmp, does not know about how many steps should be. When you use for loop statement, the number of steps can be calculated here from this information. That's why you should parallelize only for loop statement, because Openmp doesn't know about how many steps will be if you use while loop. So, and the third class of Openmp directive is synchronization. So I have said about synchronization when threads go out from for loop. There is implicit synchronization, and threads wait for each other.
It blocks like a function, so if a thread is using something, it's going to get blocked up until it finishes it.
Yes.
And then the second thread connects.
It will be blocked at the very end of the for loop. And every thread will be blocked, will be frozen here.
You cannot use the for loop until that thread is done.
By every thread.
Yes.
By every thread. But there is another point of synchronization. When you deal with shared variable, there is some issues. We have discussed these issues when we considered p threads. Do you remind that we construct critical section using semaphores?
Yeah.
So because if we have discussed that if we do not use critical section, the answer can be wrong. Yes, that's why the same is here. The same is here, but critical section created more in a simpler way, in more simpler way. In the p threads, we have we should create semaphore, we should initialize semaphore, we should use two functions, post and wait. And which one? Yes, of course. Same post and same wait. We should maybe attentively see the value of semaphores and so on. Here we just use pragma Opent critical, and between these parentheses there will be just critical section. For just one simple operation, the same can be done by pragma Opent atomic. So it will be just one atomic operation if there is just one operation. If there are a lot of operations, we can use pragma Opent critical. So between these parentheses there will be some critical section. This critical section will be executed just one thread. Other threads will wait till this one thread finish its work. Okay, let's see. Critical and atomic. So this is example, and here n equals to 1 million, I suppose. No, 1 billion. 1 billion, and S is a private, S capital is shared, and we want to summarize 1 billion times S here, and okay, integral by default is shared, and we print here as shared and integral shared, but integral was calculated without any critical section, and S should be calculated with critical section. On the critical, S plus S small. So every thread, for example, 4 threads, every thread one by one will enter this critical section and increment S capital by S small every time. Let's see what will be. 3 threads, 1 billion. Okay, 1 billion is rather big number. So we can see if we get S capital using critical section, we can see the correct answer. If we do not use critical section, wrong answer. And let's use atomic operation. You can see, by the way, it will be atomic, but doesn't matter. We can see when you use atomic, right? Correct answer and wrong answer. And we can see that we have launched 2 times and wrong answer not the same. Not the same. It's okay. So, do you have questions? And here are functions to measure the time. So, you can see that in every almost in every parallel package there is a function to measure time, because it is important. It is important to measure time, to get time, and to get, using this time, to get speed up. And this time should be measured in the correct way, because when you try to measure time using command instruments from command line or something like this, it will give you wrong answer. Maybe you can using your stopwatch, for example, but if your program will work several hours or maybe even several days, so how to measure time using your stopwatch, because you sleep.
Yes,
And you work, you travel, and so on, and your program will work this time, during this time. So it should be some instrument to measure time and give you a correct time of working. So we can see that in MPI was this function, and in Openmp yes also. In pthreads, no, because pthreads is some. We can use pthreads to parallelize your program, but initially the pthreads are not for parallelization. Was created not for parallelization, was created for operational system. So that's why it's some synthetic way to parallelize using pthreads. But Openmp and MPI initially were created to parallelize, for parallelization. So, okay, it's a simple get time on P get time before this parallel part maybe, or even in the beginning of the program, and in the end, and the difference will give you a good time, correct time. Okay. And maybe I just thinking about how to let's do some example how to check that no wait option is working. I think we can get here. N is rather big, and if we use Okay, I think the difference will be here. If every thread print time without critical, no, just time. My time is like this. My time is t out. So I make a first point of time before for loop statement and after, and every thread no difference. I think my time is it should be just t out. If there will be no wait option like this, in this way t out should be almost the same, because n is rather big, so that's mean maybe one thread will be a little bit faster than others, but it will wait for others, and t out should be approximately the same for every thread. So let's see. My out time like this, and maybe, okay, let it be. Here, the difference is rather small, yes? Let's launch it once more. So the difference in 2 digits, 2 last digits, yes? Let's turn on no wait option. So in this way, because there are a lot of operations inside this loop, so maybe one thread will be a little bit faster, and it will go out firstly, and from my point of view, the difference in time, in out time, should be greater than it was before. So, can you see the difference in the first digit after point?
Because the threads don't wait for each other at this time, right?
Now a thread does not wait. Okay, once more. It's frozen. In second digit. Okay, but when we use no wait, doesn't use no wait, the difference in 2 last digits. Yes. So no wait is does work, and maybe it will useful for you for something. So just to know. This was no wait, atomic, critical. We have discussed, I think, all things, and collapse. I just look through. Maybe I forget something. Maybe no. It seems no.
So today is going to be the last lecture, as in new material, or? Today,
yes, I suppose yes, but maybe because okay, it depends on you. If there will be time to discuss something, because I want to discuss something, for example, the symbiosis of MPI plus Openmp, it's very useful. But if you do your homework good, without any mistakes, questions, issues, so I will receive this work very fast, and it will be free time to discuss something more. But if there were issues with your work, as it was before, by the way, so maybe there will not be free time to discuss.
But like, until this presentation, it's sufficient to do the homework for.
Of course. Of course. Just discuss. Okay, I'm going to speak about task 4. It's rather simple. It's the same task as it was in MPI. To compare approaches. Because when you use MPI and you have said that it was rather simple, but you should distributed work between processes, how many and how you did this. You have sent messages between processes and so on, and to compare how it is more convenient, simpler to use Openmp to do the same work. So we can consider this task. The same integral to compute value. 1 minute, maybe once more. Compute value a shared variable interest through a critical section. By the way, we can consider a little bit. Okay, one approach, additional approach, maybe. Maybe. Yes, we can consider this approach because we have time. So this is the same description of this description is the same as it was in the first MPI program, just to compare the approaches for you and to make this simple program. And maybe I will ask you to get results not using only critical section, but in the second approach. Let's consider this approach right now. Provide access to shared variable through a critical section, and like this, and get the answer using reduction mechanism. Reduction mechanism. What does it mean, reduction? So here you can see that we use private variable as small, and to get the whole sum, we should. If you use private, it means you get some result inside every thread, and you should summarize this result between all threads in one variable. This variable is shared in this way. In this case, we just comment and see one thing. So I just for reduction, and I say S plus, and here will be S plus 1, for example. And let's see S here, what will be. Yes, vice versa. So you can see the result is correct. But one thing, as now, okay, not now, always, was shared variable. And here I increment this shared variable. This is the same integral. These lines, by the way, are the same. If I compile reduction, this line, and compile, frozen. Frozen. Don't know why. Okay, let's make n less. Okay, you can see if I compile or comment reduction statement, that means I increment variable s, shared variable, inside every thread without any, and there is an issue with the shared variable because of synchronization, because we do not use critical section when you deal with shared variable. And with integral is also the shared variable, and you can see the answer is wrong. But if I uncomment reduction, other things stay the same. Other lines are the same. I just uncomment reduction. You can see S is correct. Integral is also, as it was, is incorrect, is wrong. Why is it so? But why is it so? Because inside for loop statement, inside every thread, we increment S shared as an integral. But when we use reduction, the result from S is correct. The result of integral is wrong. Because when you use reduction, that means Openmp knows that S is shared, and this is the operation that should be when thread go out for loop. So inside for S will be private variable for every thread. So even there is a line for shared variable, when you use reduction, it will be private, even if S is capital. So take in mind that S now is private for every thread. So in this case, when S capital is private, the result will be correct inside every thread. But this result should be summarized. Yes? Every thread has some result, and these results should be summarized together. So that's why then that when threads go out for loop, this operation will be implemented. How to say? Will be implemented to every answer of every thread. And S outside for loop will again be shared. Will be shared again. So when there is reduction here, that means inside every thread as shared before will be private inside, and it will be shared outside again. And this operation will be implemented to every answer of every thread. It should be, as you can see here, it can be plus, minus, times, no, production, no, multiplying, and logical operations. Can be max, min, and so on, and logical operations. But one question. For example, if S here, what is the initial value of S when it becomes private inside every thread? What will be the initial value of this? How do you think?
The initial value of S before Open?
No, in the very beginning of okay, so S capital was shared. Now it becomes private for every thread. So what is the initial value of this private S capital in every thread? How do you think? What do you think?
Maybe the initial value of capital S is the previous thread's answer. Suppose one thread finished with S equals to 1,000.
Okay. Maybe we can. It will be useful to make a picture. So here is S capital, and for example it equals to 10, and now it is shared. If we go inside 4 with reduction plus S, for example here. Inside 4, here S, for example S plus 1, here will be private. The question is, what is the value of S, initial value of S, at the very first iteration? So S, private. So 10 is the first variant.
After the first iteration?
Before initial value. So it will be here 1. Let it be here parallel section, start parallel section. to make a little bit clear. So it was one thread, S shared, and here a lot of threads start working. Here will be all private S, like this. And after that, it will be for loop.
I would say that all of those start with 10 then.
And what is the initial value of this private S inside every thread?
10?
Okay, 10 is your answer. Other answers?
10 divided by number.
10 over n over p. Okay. Okay. So if p equals to 100, for example, or 3, or 100, or million. Yes. So, okay, this is second answer. First answer. Other opinions? 10 minus p. So it can be negative. It can be negative, yes? Okay, let it be.
10 multiplied by 2.
Oh, don't make fantasy here. So Ashish, Ron.
Whatever will be the final answer of S, right? After this for loop. You're asking about the final answer after the for loop.
No, before for loop. What is the initial? What is the value of S, private S, before for loop? 10? For 10, okay. Ron, 10. The correct answer is this initial value should be neutral for considered operation. So operation is plus. What is the neutral value? 0. If there is not the plus sign, but multiplying, for example, yes, it will be 1. Because if there will be initial operation 0 for multiplying, and you will multiply, it will always be 0, for example. This operation should not influence on answer. 0 will not influence on answer if we use plus operation. 1 will not influence on answer if we use multiplying operation. So if we use plus here, so initial value for S private inside every thread will be 0. You're right. Will be. Just wake up.
Sir, the final answer was the closest. That's p goes to infinity minus 0.
Of course, yes.
I think Santiago's was more close.
Huh?
Santiago's was the closest.
Santiago.
Santiago's is not.
No, I mean, no one was close, because if p, for example, equals to 2, 10 over p, that means initial value will be 5.
But if p equals to 10,
and
Santiago is right.
Okay, it's just in one case. But if p equals to 20, it will be minus 20. Okay, so initial value of S capital, S private inside every thread will be here 0. It will be 0, yes? But okay, what will be if S before reduction equals to something.
Then it's going to be equal to that.
No. This private always will be 0 because it is neutral operation for neutral value for operation plus.
It nullifies the value before.
Yes. But what will be if the for loop finish? Okay, like this. Like this. So here S will be equals to A, for example. It will be some answer for every thread. And what will be the value of S after for loop? What will be? So firstly, it will be something like this. Sum of I from every thread, yes, I from 1 to P, and will this answer be correct?
Yes. So we're using a reduction.
Almost, you're right, almost.
But it can be that we just override the S, which is equals to 10 at the start.
What will be, you're right, what will be with this initial value of S?
Maybe thought is going to get added to that new S. It's going to be added.
Yes, you are right, of course.
But I don't know why, so it was a guess.
S0, initial value. So S0 is initial, because it makes sense. So it was initial, some value of S capital before reduction. Why it should be rewritten? Why? We in this case, you will forget about this initial value. Why? You should keep this. So, okay, first part is calculated inside the reduction by all threads. It's okay, but we should not forget about the initial value, of course. And the initial, because there is a plus operation here, we should add this initial value to our result, to our answer.
Okay, I understand.
Do you understand? So I add this reduction mechanism, get the answer.
But that's S0. The computer automatically adds it, right?
Of course, yes. Openmp automatically add this initial value to answer from all threads, and so on. So I add this line to compute the value of integer using a shared variable like this. It will be like this, I suppose. Using yes, and using reduction mechanism. So compute the value of the integral using a shared variable into which several threads write their calculation results. Provide access to this shared variable through a critical section, and compute the value using reduction mechanism. Now you understand, yes? And plot the dependence of the speedup. Okay, so it will be task 4. Now, okay, let's make some break, and